Good morning. Let us start the morning session today. And the first speaker is Professor Mark Shimozono, and the title of his talk is Quiver Whole Littled Functions and Kostokashoji Polynomials.
It's my great pleasure to be here to honor Professor Okado. Hopefully, I'll get to the point in this lecture where I tell the story of how we met. It was an auspicious day. So this is all joint with Dan Orr. And paper finally, after many revisions, rejections, that sort of thing. You'll notice the archive date we first posted it. Five years before. It had been improved for over the iterations. But this is inspired by Professor Shoji's work on Green's polynomials for complex reflection groups. And a more recent paper by Finkelberg and Yonov sumimasen, but I'm going to probably be writing a lot of references for people, more than maybe usual. But and so what Finkelberg told me is that he wanted a sort of a coherent sheaf version of Professor Shoji's work, which is has more of a intersection cohomology or constructible sheaf kind of feel to it. And I'm more familiar with the coherent sheaf world. So when I saw this paper, then I kind of had an idea of what I wanted to do. Okay, so there's two main constructions that I'm going to talk about. So I guess part one would be Quiver-Hall Littlewood series. So these come from multi-graded modules of geometric origin. And so there'll be a little bit of geometry, but don't be scared of that. And the second part is because this kind of geometry will give you the formulas that you can really start to work with. And then the second part, I don't know exactly how long all this stuff will last, will be symmetric functions, Quiver-Hall symmetric functions built by vertex operators. So so they're going to be sort of baby vertex operators. They're all going to be sort of Heisenberg kind. Okay, so let's start with the geometry. So the first thing is Lustig's convolution diagram. And so ironically, this construction comes out of his paper where he's constructing the negative part of the universal or the quantum universal enveloping algebra in sort of a general type. He's doing this geometrically, and he's also going to construct the canonical basis. We're going to use a much more easier kind of geometry than what he gets into. And so this construction depends on two inputs. So the input data consists of two things: a sequence I1, I2 up to IM of I forgot to say the first thing I have to have is a quiver. So I just have a sequence of vertices in the quiver, and then I have a sequence of dimensions, A1, A2, up to AM. These can be assumed to be positive integers. So with this data, I'm going to make a variety. And how do I do that? So we're going to build a Q0 graded complex vector space. And I'm going to put upper dot to mean so the upper index will mean the node of the quiver. And I'm going to have to do, there's a lot of indexing, unfortunately. I'm going to try to keep that to a minimum. So the first thing we're going to do is we're going to, let's see, start with the 0 vector space. We're going to kind of go backwards through these for technical reasons. We're going to go back through these sequences and build. We're going to build a Q0 graded vector space along with a certain kind of filtration. So sort of a partial flag of these things. So how we do it? So we'll run a little algorithm for K from M to 1 down to 1. We're going to add dimension AK at vertex IK. So we're going to have these sequence of vertices, and we're going to add the corresponding dimensions at those vertices. So let's just have an example. So suppose we have a quiver like this, a 2 vertex quiver. For the first constructing, the arrows don't matter. Just let's say that K is, suppose M is equal to 5, and we have IK is 0, 1, 0, 1, 1, and AK is 1, 3, 2, 2, 1. So let's make a we're going to build it backwards, and here will be the dimension. So I'm going to have an index here like this. So an index down here like this means where am I in the filtration? And then the upper, and every one of these things is, every one of these VKs is going to be a graded vector space. And so this is dimension at 0, and then have dimension of the kth filtered guy at the vertex 1. So at the beginning, we have 0. So now I'm going to add dimension 1 at vertex 1. So this is vertex 1, so I'm going to add dimension 1 to that. Next, I add dimension 2 to vertex 1, so this 1 becomes a 3. Then I add dimension 2 at vertex 0, and then etc. So I add 1 at 3 at vertex 1, and then 1 at vertex 0. So this just remembers the graded dimensions as these things get put on. And we're going to remember, so here, let me just write this. Okay, so what I have is this filtration of this graded vector space. But if you look at individually at each vertex, you also have a partial flag at each vertex. If you just look at how the dimension jumps go at each vertex, you get a set of dimension jumps. So let's call that, let's note what these are. So here at vertex 0, we have jumps 1 and 2. Call that A upper 0 and A upper 1. We have jumps 3, 2, 1. So these, we'll want to remember that data. Now, so far, there could be a lot of more interleaving, and it wouldn't affect what happens at interleaving dimension additions between vertex 0 and 1 wouldn't change these sequences here. But it's going to change something in a second. Later data will be affected by this. So in particular, we have partial flags here. So let's see what I want to say here. So those dimension jumps at each vertex are going to define a partial flag variety at each vertex. But I'm getting ahead of myself. I wanted to say something else. So we're going to define. So in particular, we have this big. At the end, we have this graded vector space, and we're going to look at all flags that have a sort of similar shape to that one inside the big one. So the big one had dimensions 3 and 6. So inside of that, so a flag of type IA is the following. So you have we're going to have the big graded vector space to be the 0th thing. And we're going to have a decreasing. Sorry, that's not upper 0, lower 0. So we're going to have a decreasing filtration by graded vector spaces such that if I take the filter quotient, so remember this K means where am I in the filtration? So I'm comparing two neighboring graded vector spaces in the filtration, and I'm looking them at the vertex I. I want the dimension of this to be equal to AK if I is equal to IK and 0 otherwise. So basically, the way that I added the dimensions at each vertex at the beginning there, I want to add the dimensions in the same way. But here, what you should think is that this is sort of like a standard partial flag. And then we have this big ambient graded vector space. And now we're going to pick all ways to build up a similar flag inside there with the same kind of dimension jumps. And let's call it FLIA, the space of flags type IA. And as I said, this interleaving between dimensions at different vertices don't really matter. It just matters what's happening at each vertex so far. And so if you just don't get distracted by the fact you're jumping between different vertices and you look at one vertex at a time, you'll just see that we just have a product of partial flags. So so at each vertex, we have I'm going to be using lower triangular Borel. It's not so important. It's just so that the character formula doesn't have duals in it. So this is the standard Borel. This is the standard lower triangular Borel. This is a standard lower triangular parabolic. This has dimension jumps given by this A super I sequence. So up there, I said the A super 0 is 1 and 2, and A super 1 is 3, 2, 1. The dimension jumps at each vertex. Those are the sizes of the block diagonal for these block lower triangular groups. So that's the ith one, and this is inside GL of VI. So the big vector, the big graded vector space, its ith component. So we have this these groups here, and then as I said, it's really easy to see that that this is isomorphic. You're just forgetting about this distracting going back and forth and just transugate each vertex. It's just a product over I and Q, over vertices I of these so FL super I. So FL super I. So FL, the partial flag variety of vertex I is just GL VI mod. So it's just a fancy interleaved version of just a product of partial flag varieties. And so let G be the usual product of general linear groups at the vertices, the usual group that acts on your quiver Hom space, and that I'll call that E. E is the sum of the arrows, arrows B and Q1 of just linear complex vector space maps from the vector space at the tail of B to the vector space at the head of B. That's just the usual, tuples of matrices that make up the place where you can your quiver representations come from. And there's the usual action, of course, the G acts on E by change of basis at each matrix, and we have we're going to have kind of a big torus acting. So I'm going to call it TQ1. I'm going to have a copy of C star, the multiplicative group, for every arrow. This is C star to the Q1. And for B and Q1, the Bth C star acts on the corresponding Hom of going from the tail of B to the head of B, those vector spaces, by scaling. Just scale. If you're the Bth arrow, your corresponding matrix space, you just act on that by scaling by that copy of C star. And so we're going to call the group combining this G and this TQ1. So I'm calling it script G product acts on the matrix, the tuples of matrices. Okay, that's maybe more torus action than you're used to, but we're going to put it to good use. Okay, so we're almost ready to define Lustig's variety. I'm going to keep some of this stuff around. But do I going to lose this? maybe that much. Yeah. Okay. Okay, so here is the, so let me draw a picture here. We have this product of partial flag varieties here. We have these tuples of matrices here coming from the quiver like usual. Up here, we're just going to have the product and the usual projections. And inside here, we're going to have, inside there is going to be the lucid convolution diagram. And what is it? It's the pairs of these flags, and phi is the tuple of matrices. So this is, I have this tuple of partial flags and a bunch of matrices, such that if I apply I have an arrow A, so A is in Q1, and I have the corresponding matrix. I act on the flag. The K minus first guy in the filtration, and I have to tell you, and the head of the arrow, I don't want the tail, sorry, obviously. It's contained in the next. And remember that when the K increases, this thing gets smaller. Sprawl in Q1 and K1 M. So it's incidence variety. And let's call this projection P and Q. So Q, so you can act by our group, our general linear groups cross the arrow torus. You can act on this space. Of course, both of those groups act on E, and but on the partial flags, just the groups act. The torus only acts on the fiber here. And this map here, of course, is equivariant for that map. In fact, this Q is proper, and this W is smooth. Let's just tell you what it is for one loop, which is I'll be talking a lot about one loop. Example. One vertex, one loop. So let N be the sum of the dimensions. All the dimensions are happening at one vertex. And then what we have here is nothing other than the cotangent bundle of GLN mod how shall I denote it? I'll call it P sub A underscore. So the A's are telling you the dimension jumps in your partial flag. And this is just the cotangent bundle. And E is just Lie algebra GLN and by N matrices. And of course, the GLN is acting by conjugation, and the one arrow variable is acting by scaling this space of matrices. So this is a very, very, very standard thing. And the image in this case, so this map Q is the Springer resolution of a particular nilpotent adjoint orbit closure. Namely, if you take block. This is supposed to be block triangular. So if you take strictly above the diagonal, if you put arbitrary complex numbers up there, you put 0 below, and then you take the adjoint, move this thing around using the adjoint action of GLN, and then close it. Let's call this thing X sub A underscore. So this thing is a particular the closure of the conjugacy class of a particular nilpotent element, yeah. Okay, so let me just say that Lustig used this this variety W. What he did is he took the constant sheaf on this W and pushed it forward in a fancy kind of way, in a fancy kind of category, and then down to this space E, and then use the decomposition theorem to play intersection cohomology sorts of games with it. We're going to do something much more simple-minded than that. Are there any questions so far? So we're going to make some nice general modules for the product of general linear groups, multi-graded ones with nice character formulas. That's what we're going to do. So I guess that the next thing we need to do is we're going to consider the structure sheaf of this guy, and we're going to build modules for that, and we're going to take global sections and get a really nice character formula. They'll have lots of nice special cases. So this is where Dan and I depart. So Lustig only used these varieties. So we're going to look at a bunch of modules on these O of W. So what extra data do I need? So one more datum. mu1 up to mu m. And each of these mu's, mu k, is a dominant weight for GL AK. So remember, the AK was the amount of dimension I was adding at the kth step of my filtration. And so if you want, you can think of this as little partitions. Well, I mean, they're allowed to be rational dominant weights, so you can like tensor with the dual determinant, but really you can think of them as little Schur polynomials if you with little partitions if you want. So this is the extra data we're going to feed into the machine. So how is this going to affect our lives? So let me just add to this little thing here. So I keep wanting to pull it. So I'm going to add another row with these weights. So the 1, 3, 2, 2, 1 tell me how many parts my weights can have. So let's say I'll put the weight 2 and the weight 3, 2, 2, and the weight 1, 1, the weight 2, 1, and the weight 1. And we need to remember where these weights are landing, and then we're going to stack them together. So you can put zeros, you can put negative numbers as long as they're dominant, as long as you're, but there's never a need to do that because you can always just shift everything to make it positive. You know, yeah, you can put 0, 0 allowed. Yeah. So at node 0, we have just this 2 and this 1, 1. And at node 1, we have the 3, 2, 2, 2, 1, and the 1. And so what we're going to just want to, I'll call mu upper 0. Remember, the upper means at each vertex. So at vertex 0, I'm going to concatenate those weights. So just 2, 1, 1. Just stick them together like this. We really kind of remember that they're being separated like that. But so we're piling up these weights at node 1, and we get 3, 2, 2, 2, 1, 1. So these mu super things are these concatenations. And you may have noticed that I chose those concatenations to be dominant, and that's not an accident. We'll say that this data I, A, so they're your list of vertices, your list of dimensions, and your list of weights is dominant if each of these concatenated weights at each vertex are dominant. So if each mu super I is dominant. And this is the condition that we sort of the important condition we need to expect to get positive answers. Okay, so I need to so I got my extra data, my sequence of weights. Now I'm going to make a vector bundle on W, but you can just think that I'm going to make a vector space at the base point, and then I'm going to sort of move it around with the group. That's just all what this is. So over here, what I'm going to do is remember this FL is a product of partial flag varieties. We're going to consider the corresponding product of full flag varieties. It's a product of vertices I of GL VI mod B super I. So this is a product of full flags. This is the product of partial flags. And on here, on this part of, I don't have to define things this way, but it's more easier to do this. I'm going to put a line bundle, and this is just a standard line bundle. Outer tensoring a line bundle of each of these. So these mu super i's are these concatenated weights over here like this. At each vertex, I have a concatenated weight. On the corresponding full flag variety, I make the standard line bundle of that weight. That's this L mu super I. I take this outer tensor product, so they're just going over separate things and separate components, and that line bundle is on this space. So that's a totally standard thing. And then what I want to do is this. I'm trying to decide how to denote this. W sub mu sequence of this down notation means a sequence of weights. So I'm going to make this is the vector bundle I'm going to define. It's let's call this map here R. Then I'm going to take this line bundle and push it forward by R and pull it back at P. And that's the definition of this thing. So rather than explain how to track the whole character computations that goes through, I'm going to instead give examples. But okay, so this vector bundle here is living on W, and what we're going to do is we're going to push it to E, that's because E is a affine variety, the same thing as taking global sections. And we're going to take the Euler characteristic like you always do, because that's the only thing you can directly compute. And so define the Quiver-Hall-Littlewood series. So it's generally an infinite series, a symmetric infinite series, chi IA sub mu. And it's defined to be this alternating sum of, so everything in this Springer map Q is equivariant respect to this. This is a script G. That's a product of the general Lewis groups at each vertex with the torus coming from all those arrows of the Pieth-Schiff cohomology. So that's the higher derived functors of taking global sections. But okay, that may sound a little bit scary if you haven't learned about it, but the brilliant thing is that you can view this possible monster here as just being a bundle of the product of flag varieties. And BOT tells you how to compute the global section, how to compute the cohomology in that situation. It's a formula everyone knows, actually. So so anyway, because the indexing is even more complicated, if I tried to write down all the roots that I then need to do, I'm not going to do that in general. I'll just do an example. So this thing is a virtual character, and I'm going to write down the formula for this virtual character. Well, hopefully didn't blow too much stuff. Example. The single loop again. N is the sum of so the dimension jumps AK. N is the sum of dimension jumps. And rho is the vector n minus 2 down to 0. Your usual thing. And we're thinking of it as being in n tuples of integers. And this is of course, the GLN weight lattice. And let J be the anti-symmetrizer. So sum over W in symmetric group with -1 to the length of W. W, this is that operator. And then we'll let mu be just to concatenate all of the mu k's. So maybe we have a sequence of weights, and we're just going to concatenate them. There's only one vertex to talk about. And we do that, and we get the following formula. Chi thing is bialternate. So divide by the Vandermonde, or the Weyl denominator of type A, of the anti-symmetrization of, we have x to the rho plus mu times the product over all positive roots. I'm sorry, not all positive roots. Those that are in the, so 1 over minus t x to the alpha. So not over positive roots. Say our Say that our A underscore was 3, 2, 1. Then your Levy is this block diagonal 3, 2, 1 thingy. And the roots that you want are the, if you take, so this is the nil radical of the, so our parabolic, if we, maybe I drew the, well, those are the correct set of roots. Since I defined this to be lower triangle, this is kind of backwards. So maybe I should just, I should say, these shaded positions are where you take your positive roots from. Not all positive roots, just the positive roots here. So, and let me just tell you what this is in the first non-trivial case. When you have 1, 1, what do you get? So T is, okay, T is, remember we have a T variable for every arrow. We have a single loop, so it's the torus parameter for that arrow. Yeah, there's one matrix, and there's one arrow, so there's one scaling parameter, and that's that scaling parameter. So the first, so if n is equal to 2, and a is equal to 1, 1, so just put, I have a single vertex, I put one dimension there, another dimension there. Then this is the answer. This character is equal to the sum over k greater than 0 of t to the k the character of highest weight k negative k of x1 and x2. If you don't like that, then you can take the determinant x1, x2, take the negative kth or the kth tensor power of the dual, and then have the sure polynomial of 2k0. That's 2. So notice that it's infinite sum, but this thing is locally finite. In each degree, you get a finite thing, a finite amount of stuff. You don't get some crazy infinite amount of stuff. In each graded. No, see that script G there? That's the product of GLs with a product of C stars. The C stars, each of them. Okay, I probably forgot to say that the representation of TQ1 is isomorphic to and so for each arrow, I have a corresponding C star action, and then I have a corresponding thing to remember its character. And in this case, we only have one of these, and that's the thing that's in there. Yeah. Is that... Okay, so these things are infinite, but not in a super bad way. Okay. Oh, so the first main thing you have to know about is when do you expect these to be positive? So vanishing conjecture, it's sort of an obvious thing to expect if you had some experience with this. So this is in not that big of a deal, but we said it. So if our data is dominant, then these higher cohomologies are 0 for all peak when equal to 0. And that means that in your alternating sum, all the negative signs can't happen. So an immediate corollary of this is whenever you can prove this higher vanishing, you get positive answers, which so there's two kind of worldviews here. The geometer's worldview is the only problem here is to prove this vanishing. And if I prove the vanishing, then I'm very happy. The combinatorialist says, I want to know what that answer is. I want to build some tableau or something like that, and some kind of statistic like energy, which gives me this answer. And I'm only happy if I get that answer. So there's sort of two kinds of important positivity problems here. One is this geometric statement, and the second one is the combinatorial statement. And depending on who you are, you like one or the other one better. And I won't judge you either way. Okay. Yeah. So let me now launch into a whole long list of examples, and some terminology. The Borel case is when all those parabolics are Borels. So the Borel case is when a sub k is equal to 1 for all k. So another way of saying that is your list of weights are all single rows. So a combinatorialist kind of knows that this is going to be, if there's going to be an easy case, this is going to be it. And that we're going to call the parabolic case just the general case. So now is going to come a really long list of contributors. So example. So I'm going to make a whole list of people, what they said about the, sumimasen. I forgot to. I forgot to define the isotypic components and call them Quiver-Costa-Shoji polynomials. That was a huge blunder. Let me fix that. Whoops. So you have to rewind your notes back to this page. So this is a product of general linear groups and a bunch of tori. So the product of linear groups, but this thing has this action of a bunch of general linear groups. So you can take its isotypic decomposition. And so for every general linear group, you're going to have a dominant weight. And so you're going to have, and so there's one at each vertex. So lambda dot, remember the dot means at each vertex, you're going to have a partition or whatever, a dominant weight. So that's what this means. And we're going to have the corresponding irreducible character, which is a bunch of Schur polynomials in different sets of variables, and one set of variables at each vertex. And then we're going to have the coefficient. And the coefficient is going to carry this multi-grading. And so we'll call that K. Better get my notation straight. I, A, lambda dot mu lower dot of TQ1. So this TQ1 is my abbreviation for all of different error variables. For every error you have another T. So this thing is a product of general linear module and multi-graded, and this multi-graded coefficient here, I'm going to call that the Quiver-Koska Shoji polymer. Okay, so now let's wind back forward. Okay, so example. So the first thing we're going to talk about, single loop, which is actually the most fundamentally important special case. It's not the most complicated, but it's the most important case. And we're going to start with the Borel case. And in that case, what you get for these Krivokazu-Shoji polynomials is the Koska-Fuchs polynomial. And so there's a bunch of people I'm going to quote here. Lasker and Schutz and Berger. And 78, give a tableau formula. And these guys actually knew about type A crystal bases, and they also knew about affine. They actually had the equivalent of 1 row Kirillov Verstetiken. Morally speaking, they had this already in 78, and this was giving them their. So this is brilliant work before its time. So this is a positive answer in terms of tableaus. There's the Kirillov Verstetiken. This is in 86. The fermionic formula. Some of you may know these as ribbed configurations. It's unlike any formula. If you have it, it's unlike any formula you've seen before. When you see it, just go unbelievable formula. There's a more geometric version. So Ronnie Berlinski. This is in around 89. Filter the weight space by principal nilpotent. So if you take the usual GL weight space, the Muth weight space, and then you act on it by powers of the principal nilpotent, you see how fast stuff gets killed. That jump polynomial is Koska-Fuchs. That was Ronnie Berlinski. She did it for more general type. And the vanishing, maybe I should up the board just a tiny bit. Well, I'm actually not sure who did vanishing in this case, but it certainly follows from Brer in 94. His name is going to come up later. And then we have affine crystal theory, Nakayashiki and Yamada. This is in 95. So one-dimensional sum for tensor product of KR crystals of the form 1 mu k. So so they realized that you could make the Koska polynomials by these KRs. But as I said, like secretly, the Laskin Schutz and Berger technology has this knowledge already. I claim that that's true. Now let's move forward to the parabolic case. Oops. We're giving a whole long list of names here. So these, so I'm going to give me and Yoshi Wayman credit for this. And that was, well, our paper appeared in 2000. That might be part of a comment later. So there's a bunch of special cases. If all of those, remember that sequence of partitions, if they're all single columns, then you get Koska-Fuchs with reversed grading. I'll call that Koska reversed. And the interpretation of this are intersection cohomology, local intersection cohomology of these nilpotent adjoint orbit closures, and that's Lustig in 81. There is a very tricky tableau formula. Lascaux, which gave me the idea of what to do in more generality. This is in 89. There's a using Tanisaki ideal, Tanisaki generators. So if you take this nilpotent adjoint orbit closure and intersect with the Cartan subalgebra, you get a graded module for the symmetric group, and you can ask about its isotypic decomposition. And this is studied by Garcia and Paccese. And this is the first time I saw the vertex operators appearing. So Garcia was the guy who I saw that from. And again, 1D sum for tensor product of KRs of the form single column KR. So we have AK but one. Okay, and this is again, Nakashiki Yamada is that. And then comes the time when I'm talk about how I met Professor Okado. The all rectangles case. Oh, by the way, I forgot to say that everywhere I'm assuming the dominance, like you have to order your partitions in the correct order so that and they have to stick together to be a partition. In all rectangle case, UK is equal to a rectangle, AK by DK for all K. So so I proved that that the geometric character has a tableau formula. I'll say 2001. And there's also the fact that the tableau formula equals 1D sum of KR tensor product KR crystals in type A. Because that's the end of my talk. So this is exactly what I was about to say when I met Okado. So I do need to say that on Schilling and Ole Warner, they're part of the story, though, that I was about to say. 19. And these dates tell you like who publishes faster, physics journals or math journals. This is 99, and And I had the same combinatorics. Oops. Okay, so sorry, I went half minute past. That's it for today.
Thank you. Any question or comment?
What do you want to add more?
I think I do want to tell the story of how I met Okado-san.
Oh.
So what happened is I was like maybe 1 year into my first tenure track position, and I was invited by Kailash Misra to give a talk in NC State. So I give this talk about all this rectangle combinatorics, and Okado-san is in the audience. And so when I go back and I'm sitting in this office for the visitor, just sitting there, he says, by the way, you might want to look at this preprint on the archive. And there was a preprint of Schilling and Varnar. And I started looking through it, and I saw like isomorphic combinatorics. I started getting sad. See more and more pages, get more sad, more sad. I mean, they didn't have the connection with the geometry, but still, I mean, probably at the time I was most proud of the combinatorics, and so I just sad. But the story has a shining ending. I just looked at MathSciNet, and there's 20-something Schilling Shimozono papers, and 6 of them also have Okado on there too. So I met Anna through Masato, and also, of course, I met Masato, and so he's indirectly responsible for a decent percentage of my publications. So, domo arigatou gozaimasu.
Other comments or question?
Is there some natural interpretation of the rig configurations in the geometry?
I have no idea.
Other comments?
Is there some way you can, well, I guess you'd have to extend the geometry to get the Cauchy formula for Hall Littlewoods?
Which Cauchy formula? Which Hall Littlewoods too?
I guess which the one with your work with Sasimoto and with that Cauchy formula. That's good. Yeah.
Yeah, so sorry, I'm a beginner of this field, but the Cauchy formula we used is that something the product of the sum of product of whole little root over the whole partition is equal to the some product of something. Yes, something like Q product consisting of Q Pohohammer symbol, and then
Product of what? Sorry.
Q Pohohammer symbol.
Yeah, I'm not familiar with that. Maybe we can talk about it afterwards.
Thank you.
Other comments? Then let's thank the speaker again.